the night of the 17th of March, 1943. A Panzer IV rumbles through the narrow streets of Medellin, Tunisia, its commander scanning the rubble-strewn approaches with practiced vigilance. The exhaust note changes pitch as the driver downshifts, the 25-ton machine slowing to navigate a collapsed wall. At precisely 0347 hours, the tank's right track connects with something small, something seemingly innocuous lying amongst the debris. There is no explosion, no flash, no percussive blast that might alert the crew to danger. Instead, there is only a sharp metallic crack, barely audible above the diesel engine's rumble, followed by an irregular grinding that sends vibrations through the hull. The driver attempts to accelerate. The engine screams. The left track continues its relentless rotation, but the right track has ceased all forward motion. Within 90 seconds, the Panzer sits immobile, slewed at an awkward angle, transformed from a mobile weapon platform into a stationary pillbox. The crew has no idea what has stopped them. They will not discover the answer until dawn reveals a small metal object, no larger than a biscuit tin, crushed beneath their starboard track assembly. The problem facing British forces in North Africa had reached crisis proportions by late 1942. German armour dominated the battlefield with a mobility advantage that conventional anti-tank mines could not adequately counter. The mathematics were brutal and unforgiving. A standard British anti-tank mine required approximately 6 kilograms of explosive, demanded careful emplacement by trained personnel, proved detectable by enemy mine-detecting equipment, and carried substantial risk to the soldiers laying them. Production capacity limited availability. Supply chains struggled to deliver sufficient quantities to the front lines. The statistical reality proved devastating. British forces could not produce, transport, or deploy enough conventional mines to create effective barriers against German armoured advances. Tank commanders had learned to identify likely mining locations, to follow cleared paths, to probe suspicious ground with expendable vehicles. The existing anti-tank mine represented a known quantity, a predictable threat that could be managed, circumvented, or accepted as an operational cost. British military planners needed something fundamentally different. The challenge seemed insurmountable. How does one stop a 25-ton armoured vehicle without using the traditional methods of high explosive penetration or catastrophic damage? The answer emerged from an unlikely source, from an understanding not of how to destroy a tank, but of how a tank actually moves. A tracked vehicle depends entirely upon the integrity of its track assembly. Each track comprises dozens of individual steel links, pins, and connectors, assembled in an endless loop around drive sprockets and idler wheels. The entire system operates under tremendous mechanical stress, with each link bearing loads of several tons during normal operation. Damage to even a single link can render the entire track inoperative. The solution required no sophisticated explosive train, no shaped charge, no armor-piercing projectile. It required only sufficient force, applied at precisely the right moment, to sever a track link. The device that emerged bore the prosaic designation anti-tank mine, non-metallic, Mark I, in official documentation, though soldiers in the field knew it by various names: the track buster, the tank crippler, or most commonly simply the clam. The design proved deceptively simple, a masterwork of mechanical engineering that achieved extraordinary results through basic physics rather than chemical energy. The core mechanism consisted of a spring-loaded striker assembly enclosed within a pressed metal or bakelite housing, measuring approximately 12 centimeters in diameter and 4 centimeters in height. The spring, manufactured from high-carbon steel and compressed to exert approximately 200 kilograms of force, weighted beneath a pressure plate requiring only 9 kilograms of applied weight to trigger. When a tank track passed over the device, the pressure plate compressed, releasing the striker to punch upward with tremendous force against the track link directly above. The striker, fashioned from hardened steel and shaped to a chisel point, concentrated the entire spring force onto an area of less than 1 square centimeter. The result proved devastatingly effective. The striker punched through or severely damaged the track link, causing immediate mechanical failure. The genius of the design lay not merely in its mechanical simplicity, but in its exploitation of the tank's own weight against itself. A Panzer IV exerted a ground pressure of approximately 0.9 kilograms per square centimeter across its track width, meaning that even a small portion of track passing over the mine delivered more than sufficient force to trigger the mechanism. The striker fired upward with enough energy to penetrate track links made of manganese steel, which typically measured 8 to 12 millimeters in thickness. Laboratory testing revealed that the device could reliably damage or sever track links on every German and Italian tank then operating in North Africa. The damaged link would continue to function briefly, perhaps for 1 or 2 full rotations, before the weakened structure failed completely under operational loads. This delayed failure added a psychological dimension to the weapon's effectiveness. Crews could not immediately determine what had damaged their vehicle, and the progressive nature of the failure meant that tanks often became immobilized some distance from the actual mine strike, complicating recovery efforts. The development program proceeded under the direction of Lieutenant Colonel Millis Jeffress, an officer who had already earned distinction for his work on irregular warfare devices and improvised munitions. Jeffress understood that the mine's value lay not in spectacular destruction, but in operational denial. A destroyed tank could be dramatic, but an immobilized tank achieved strategic effects nearly as valuable whilst requiring far less material investment. His design philosophy emphasized producibility, deployability, and reliability over raw destructive power. The initial prototypes emerged from workshops in early 1942, with field trials conducted against captured Italian vehicles in Egypt. The results exceeded expectations. Mines disabled test vehicles with near-perfect reliability, and the non-explosive nature of the weapon meant that failures, when they occurred, posed no danger to friendly forces. Manufacturing began in earnest by mid-1942, with contracts distributed amongst several British firms experienced in precision metalwork and plastics production. The relatively simple construction allowed for rapid production scaling. A single mine required approximately 450 grams of steel for the striker and spring assembly, with the housing manufactured from either pressed tin or molded bakelite, depending on material availability. Production costs proved remarkably modest, approximately 4 shillings per unit, compared to 32 shillings for a conventional high-explosive anti-tank mine. This economic efficiency transformed tactical possibilities. For the cost of 1 conventional mine, British forces could deploy 8 track-busting mines, creating defensive belts of unprecedented density. By December 1942, production exceeded 50,000 units monthly. By the conclusion of the North African campaign, more than 600,000 mines had been manufactured and shipped to theatre. Deployment doctrine evolved rapidly as units gained experience with the weapon. Unlike conventional mines, which required careful spacing and emplacement in prepared positions, the trackbuster could be scattered semi-randomly across probable approach routes. The mines proved small enough that a single infantryman could carry a dozen in a standard pack. Their light weight, just over 1 kilogram each, meant that even small units could establish extensive minefields quickly. The non-explosive nature eliminated the primary danger associated with mine-laying operations: accidental detonation during handling or placement. Soldiers could toss the mines from cover, scatter them across roadways, or even drop them from low-flying aircraft. The psychological impact on German tank crews proved substantial. Armoured vehicles that struck conventional mines typically suffered catastrophic damage that announced itself with violent immediacy. The trackbuster offered no such clarity. Crews heard only a small sound, easily dismissed as debris or uneven ground, followed minutes later by inexplicable mechanical failure. The uncertainty corroded confidence. Tank commanders could not know whether they had struck one mine or a dozen, could not determine whether their vehicle would fail immediately or kilometers down the road. The first large-scale deployment occurred during the Second Battle of El Alamein in October 1942, though track-busting mines played a supporting rather than starring role in that engagement. Montgomery's forces employed approximately 20,000 mines across the defensive sectors, mixing them with conventional anti-tank mines and anti-personnel devices to create a defensive matrix of fearsome complexity. German armor attempting to navigate the cleared gaps found their advance disrupted not by spectacular explosions, but by an accumulating toll of disabled vehicles. A panzer battalion that began an advance with 40 operational tanks might find itself reduced to 25 mobile vehicles within an hour, not through combat action, but through mechanical attrition. The disabled tanks created obstacles that complicated movement for following vehicles, generated confusion in command networks as unit cohesion disintegrated, and demanded recovery assets that were themselves vulnerable to artillery fire. The German response evolved through several phases. Initial encounters produced bewilderment. Crews could not understand what was disabling their vehicles. Intelligence officers collected damaged track links and discovered the striker marks, prompting a search for unexploded mines. When specimens were recovered and analyzed, German engineering staffs initially dismissed the devices as ineffective nuisances, a judgment that combat experience would comprehensively refute. By early 1943, German armored units had developed countermeasures of varying effectiveness. Some units attempted to deploy expendable vehicles ahead of main formations to trigger mines, but the trackbusters' light trigger weight meant that even motorcycles and small vehicles could detonate them, providing advance warning without necessarily clearing paths safe for heavy armor. Others tried to use explosive demolition charges to clear suspected minefields, but the mines' small size and non-metallic construction options made them difficult to detect even when their approximate locations were known. The most effective German countermeasure proved to be the simplest: acceptance. Tank commanders learned to expect a certain percentage of mechanical casualties from track damage and planned operations accordingly, maintaining larger reserve formations to compensate for anticipated losses. The Soviets observed British employment of track-busting mines with considerable interest and rapidly developed their own variants. The Soviet TM-35 mine included a non-explosive pressure-triggered track breaker as one firing option, though Soviet doctrine emphasized explosive anti-tank mines more heavily than did British practice. American forces evaluated captured British mines, but chose not to adopt the design for their own use, preferring conventional high-explosive anti-tank mines that offered the possibility of catastrophic kills rather than mere mobility disruption. This doctrinal difference reflected broader philosophical divergences in anti-tank warfare. British forces, operating with constrained logistics and limited industrial capacity, valued weapons that achieved maximum effect with minimum resources. American forces, benefiting from overwhelming industrial production, could afford weapons that expended more resources per target whilst delivering more dramatic results. The Italian campaign witnessed extensive use of track-busting mines by both British and Commonwealth forces. The mountainous terrain and limited road networks created ideal conditions for their employment. A single disabled tank on a narrow mountain road could block an entire column for hours, transforming minor obstacles into major operational delays. British forces defending prepared positions could emplace thousands of mines across approaches in a single night, creating defensive barriers that required minimal maintenance and posed negligible risk to friendly forces. The Germans, increasingly pressed for resources as the war progressed, began manufacturing their own copies of the British design by mid-1943. German versions employed slightly different spring specifications and housing materials, but operated on identical principles. The appearance of German-manufactured track breakers in Italy represented a telling acknowledgement of the weapon's effectiveness. Statistical analysis of the mine's operational impact presents certain challenges. Unlike high-explosive anti-tank mines, which typically produced easily documented catastrophic kills, track-busting mines generated disruption that manifested across multiple dimensions. A disabled tank might be recovered and returned to service within hours if recovery assets were available and enemy pressure remained light. The same disabled tank might be abandoned as a total loss if recovery proved impractical under combat conditions. Comprehensive records from the North African campaign suggest that track-busting mines accounted for approximately 15 to 20% of all German armoured vehicle losses attributed to mining, a figure that understates their strategic impact. The true value lay in operational tempo disruption, in forcing enemy armoured formations to slow advances, to commit recovery assets, to maintain larger reserves against expected attrition. These effects proved difficult to quantify, but profoundly influenced campaign outcomes. The mine's design influenced post-war anti-tank mine development across multiple nations. The recognition that mechanical damage could achieve valuable results without requiring explosive payloads prompted experimentation with various non-explosive or reduced explosive anti-tank devices. The Soviet PMN-4 mine, introduced in the 1960s, incorporated non-explosive track damage mechanisms alongside its explosive charge. Modern anti-tank mine design increasingly emphasizes mobility denial over catastrophic destruction, reflecting lessons first validated by the British track buster in North African sands. The concept of using an enemy's own weight and momentum against itself, of applying force at precise points of mechanical vulnerability, represents the enduring principle in mine warfare. Several thousand British track-busting mines survived the war, stored in ordnance depots across the former empire. Many remained in service with various Commonwealth armies well into the 1960s, valued for their reliability, economy, and continued effectiveness against tracked vehicles that had grown heavier but retained fundamentally similar track designs. Demilitarization programs in the 1970s destroyed the majority of remaining stocks, though specimens survived in military museums across Britain, Australia, Canada, and New Zealand. The Imperial War Museum in London maintains a cutaway example that reveals the elegantly simple spring and striker mechanism. Ordnance disposal teams continue to encounter buried examples during construction projects across former battlefields in North Africa and Italy, their non-explosive nature ensuring that even 70-year-old mines pose minimal danger when discovered. The broader significance of the track-busting mine extends beyond its immediate tactical applications. The weapon represented a philosophical approach to military problems that prioritized elegant simplicity over complex sophistication. Engineers designed a device that required no explosive, no complex fusing mechanism, no sophisticated materials or difficult manufacturing processes. It could be mass-produced by semi-skilled labor using readily available materials. It could be deployed by any soldier with minimal training. It functioned reliably under extreme environmental conditions, from desert heat to mountain cold. It posed negligible risk to friendly forces even when employed in hasty or improvised defensive positions. Yet this simple device achieved effects comparable to weapons requiring far greater investment in design, manufacture, and deployment. The trackbuster exemplified a category of weapons that emerged during the Second World War, devices that achieved maximum effect through minimum means, that exploited careful analysis of enemy vulnerabilities rather than brute force application. This design philosophy produced some of the war's most effective weapons, from the sticky bomb anti-tank grenade to the Piat launcher to various shaped charge munitions that defeated armor through physics rather than explosive mass. The track-busting mine belonged to this distinguished lineage, a weapon that succeeded because its designers understood that stopping a tank did not require destroying it, that mechanical failure could prove as decisive as catastrophic explosion, that operational denial represented a legitimate and valuable objective. The evolution of deployment techniques throughout the war revealed the weapon's versatility. Early employment followed conventional mine-laying doctrine, with engineers marking fields, recording positions, and maintaining defensive belts according to established procedures. Experience rapidly demonstrated that such formality proved unnecessary. The trackbuster's safety characteristics allowed for far more casual employment. Infantry patrols departing forward positions would carry a dozen mines and scatter them opportunistically along likely enemy approach routes. Armored car crews would toss mines from their vehicles whilst conducting reconnaissance withdrawals, sowing confusion in pursuing enemy formations. Artillery observers, forced to abandon observation posts under pressure, would scatter mines around their positions as they withdrew, ensuring that enemy forces occupying those positions faced subsequent difficulties. This opportunistic employment created a cumulative defensive barrier far more extensive than formal minefields alone could achieve. The psychological dimension of trackbuster employment deserves particular emphasis. German tank commanders had learned, through hard experience, to recognize and respect conventional minefields. The distinctive markers, the cleared lanes, the defensive positions supporting the minefield, all provided tactical intelligence that informed decision-making. The trackbuster undermined this learned battlefield literacy. Mines appeared where no minefield should exist, in locations that seemed tactically nonsensical, scattered with apparent randomness across terrain that conventional mining doctrine would ignore. This unpredictability forced German commanders to treat every advance as potentially mined, to slow operations, to probe cautiously, to maintain heightened vigilance that exhausted crews and consumed operational tempo. The mental burden of constant uncertainty proved as valuable as the physical damage the mines inflicted. Production statistics reveal the weapon's economic efficiency with striking clarity. Between mid-1942 and war's end in Europe, British manufacturers produced approximately 2.3 million track-busting mines at a total program cost of roughly £460,000. This investment, equivalent to perhaps £25 million in contemporary purchasing power, purchased a capability that materially affected armoured operations across 3 theatres of war. For comparison, the British anti-tank gun program consumed approximately £180 million during the same period, producing weapons that required crews, ammunition, transport, and support infrastructure. The trackbuster demanded none of these ancillary investments. Once manufactured, it required only delivery to forward units and dispersal across the battlefield. No ammunition resupply, no crew training beyond basic handling instruction, no maintenance beyond ensuring storage in dry conditions. The weapon represented military logistics at its most efficient, maximum effect from minimum continuing investment. Field modifications and improvised variants emerged as soldiers adapted the basic design to local conditions and requirements. In Italy, engineers discovered that trackbusters could be effectively deployed in wooden boxes that simulated anti-personnel mine casings, encouraging enemy mine-clearing teams to waste effort on devices that posed no danger to infantry whilst overlooking the actual track-breaking threat. In North Africa, some units experimented with burying mines beneath a thin layer of sand, ensuring that even careful visual inspection would miss them. Others found that placing mines in shell holes and shallow depressions increased trigger probability, as tank drivers naturally steered to avoid obvious obstacles and thus concentrated their vehicles' paths in predictable patterns. These tactical refinements, developed through practical experience rather than formal doctrine, demonstrated the weapon's adaptability to diverse operational contexts. The device reminds us that warfare's most effective innovations often emerge not from revolutionary technology, but from revolutionary thinking about existing technology's applications. The engineers who conceived the trackbuster did not invent new materials or discover new physical principles. They simply looked at a tank's track assembly with fresh eyes, recognized a fundamental vulnerability, and designed a weapon to exploit that weakness with ruthless efficiency. In doing so, they created a device that immobilized thousands of enemy vehicles, disrupted countless operations, and influenced anti-tank mine design for generations, all whilst requiring less steel than a single rifle and costing less than a pair of military boots. The small pressed metal cylinder that stopped German armour in North African darkness embodied principles that transcend its specific historical moment. It demonstrated that effective weapons need not be complex, that economy of means can prove more valuable than excess of force, that understanding an enemy's weaknesses matters more than overwhelming his strengths. These lessons resonate across military history, from ancient siege warfare to modern asymmetric conflicts, a testament to the enduring truth that human ingenuity, carefully applied to well-understood problems, can achieve results that brute force alone cannot match. The Trackbuster's legacy persists not in museums alone, but in the continuing recognition that sometimes the most devastating weapons are those that whisper rather than roar, that disable rather than destroy, that achieve their effects through elegant simplicity rather than spectacular violence.